Hello everybody, I'm Andrea and I'm a material engineer working at PULab, which is the 3D printing laboratory of the Polytechnic of Milan. I'm going to present the ongoing project about remanufacturing of end-of-life composite material via 3D printing. I will start from the European project which I work for. The aim of Fiber Reuse project is to investigate different possible paths for the circular economy and remanufacturing composite material. And we are focusing on fiberglass composite, which is the main constituent of a wind turbine blade. I show you the first implant located in Denmark that was dismantled in 2017, and has many implants are running 25 years old and will be probably dismantled. The recycling of fiberglass composite is a not point, not problem for the environment. Here you can see a pilot project where in Denmark used the wind blade to produce a noise barrier in the roads. But there are many ways to recycle composite. We can create energy by burning them and recovering the long fibers, or use chemical to recover the fibers and dissolve the matrix, or mechanically grinding to produce a powder. And maybe the best solution will be to reuse them or to repair, so to increase the lifetime of the component the most. We are working on mechanically recycled fiberglass that we can reformulate, and so we can add this material to a resin as a filler, and we produce thick pasties that can be 3D printed. And thanks to the design freedom of this technology, we can find a new application for the material. Let's see the properties of this material. First of all, premise. Here you can see the main component of our blend: a photoactive resin, a reactive diluent, a photoinitiator, and a thermal initiator. These components create a resin system at which we can add a recycled material in form of fine powder. In order to find the best condition for mixing the material, we define a grid of formulation to make the tests. And experimentally, we have been able to define which formulation can be mixed with a mechanical stirrer, which can be mixed with a thick past mixer like a bender, and which cannot be mixed to produce an homogeneous material. Then we selected 15 formulation to test the rheological behavior. And as you can see, all the formulation exhibit a Newtonian behavior at low shear rate and a pseudoplastic behavior at high shear rate. From the experimental data, we have been also able to define a printability window and also to exclude some formulation to the next test. Even though we have a printable material, we saw that some formulation produce bad surface finish in the 3D printed object. And for example, here you can see that the formulation with 45% of recyclate on the right turns out badly from the 3D printing process. By adding the reactive diluent to the resin, we can enhance we can produce a better finish, an object with a better finish, even though we have still an high content of recyclate. Since we use a photoactive polymer, we tested the reactivity, and as you can see, for increasing the content of recyclate, the UV conversion decrease for the 3D printable inks, and so part of the monomer are not reacted. Moreover, after 3D printing, the material is still photoactive, and this is due to low rest time under the UV light during the process. For this test, we are able to define an optimal curing cycle, and going from the 3D printable inks to the 3D printed object, we have the material that is partially polymerized, and in this way the shape retention is assured. Then, with an UV post-curing, we ensure that all the photoactive resin is the photoactivity, is extinguished, And then with the thermal post-curing, we complete the cross-linking of the matrix. In order to be sure that all the material was cross-linked, we perform also a gel percentage, and the higher is the gel percentage, the higher is the cross-linking density, and so the lowest is the unreacted monomer. As a benchmark, you can see the result of the material filled with virgin glass fiber, that is good, 100%, and even though the result for the recycled composite is good, more tests are needed to reach a higher gel content. Moving to the mechanical properties, here you can see the elastic modulus for the neat resin and for the composite materials. As you may notice, even with the 45% of recyclate in the material, the glass fiber content is very poor, and the mechanical properties are quite similar to the neat resin. On the other hand, for virgin glass fibers, we have a very high benchmark. Anyway, considering the real content of glass fiber, the results are comparable with the help-inside model prediction. For what concerns the failure properties, the most evident effect is the decrease of toughness of all the composite sample compared to the neat resin. This result can be attributed to a low adhesion between the fibers and also to the presence of voids in the samples. However, as many paper confirms in literature, the mechanical properties of 3D printed composite material are better than casted material, since the fibers are preferentially aligned in the extrusion direction, increasing the toughness in that direction. All the tests have been made with the recyclate batch A from construction industry, and this recyclate is very pure in glass fiber content. But now, considering the new recyclate that we received from end-of-life wind turbine blades, the content of glass is very high, and we have been able to measure the recycled glass fiber length and radius, and in this way we can calculate with Alpine model the elastic modulus. And so here you can see that even though the filler content is 45%, with the batch B we can reach higher content of glass fiber, and so the predicted elastic modulus is higher and comparable with the mechanical properties of a composite made with virgin glass fibers. Until now, I've spoken of 3D printing, and now I will go through the process development. What is frugal innovation? Frugal innovation is a way to find cheaper solutions to produce quality results. With this approach in research, it is possible to iterate more rapidly and so to do good research even with low-cost hardware and software. For this reason, we use low-cost 3D printer that in 2016 in our research group was modified to become a 3D printer capable of extruding photoactive polymers. We start from that configuration, and we saw that with the complex geometry, some points of the model were not reached by the UV light, and so we have a bad result. For this reason, we decided to change the UV LED apparatus, putting 3 LED, in order to have a more distributed light, and the results were good. And here you can see the print and the final object that was produced, and it is quite good. But we have seen that during 3D printing we will not reach the complete does not complete the photopolymerization of the material, and so we need an UV post-curing. In order to overcome this problem, we are now testing a side UV LED apparatus, where after each layer the object can rest under it for some seconds and complete the photopolymerization. One of the main features of UV-aided 3D printing is the possibility to print without supports, even when they would be needed in the FDM 3D printing process. And in this video, you can see that the 3D model that is kind of a spiral grow up without support, and the angle between the building plate and the overhang surface is lower than 30 degrees. So this is possible because the material is rapidly cross-linked and as it goes out of the nozzle. For the design point of view, there are some applications that might be of interest for this material. Here you can see some sketches of rest areas and outdoor architecture that were aspired to wind turbine blades with the spirals and helical shapes. And here some concept for an amusement park with main entrance or attraction. With 3D printing, we have been able to print two models, one of an external architecture, and on the right, the entrance of an amusement park, inspired to the entrance of an attraction at the famous in Italy Gardaland. The forecast of the wind blade waste for 2012 tell us that we will have a lot of material. For this reason, we have to remanufacture the material for producing big component if you want to use really this material to eliminate the waste. And 3D printing can be used to produce very tailored and unique parts, even of big dimension, as some 3D printer producer or design studio are doing now. So, in conclusion, we understand that the advantages of using a frugal innovation is a good way to use also 3D printing as an approach to rapidly adapt a system to the needs of the material in this research. We saw a possible remanufacturing approach that Fiber Use European project is experimenting. The recyclates can be processed in a wide range of formulation, showing good result in terms of printability and surface finish. And the UV-aided 3D printing process lead to the construction of a complex structure. The scale-up of the process have been also foreseen by design concept and the availability of big volume 3D printer. And thank you for the kind attention.